Hi, my name is Hui and I will represent for my team and present our project, the Multi-Index Search with LLM. We have designed a fault-tolerant asynchronous RAG pipeline tailored specifically for e-commerce return and dispute resolution. It executes microsecond-level document retrieval combined with our automated generative arbitration. Now, let's start with the real-world context. E-commerce platforms handle thousands of unstructured dispute claims daily. These inputs have massive semantic variance. Customers use highly diverse vernacular phrases to describe physical defects, like saying torn seams instead of incorrect fit. Traditional legacy monoliths push all these operations through a single shared thread. This creates a severe pipeline ceiling, leading to immense resource contention and cascading system crashes under heavy load. To understand the cause of cascading failures, look at the historic AWS outage in December 2021. A single congestion block within the internal control plane led to thread saturation, holding network sockets wide open. Because upstream services kept retrying requests continuously, they generated a self-inflicted DDoS wave. This proves that synchronous, tightly queued components are highly dangerous at scale. Our solution introduces a multi-index breakthrough in a legacy database. Querying direct layers forces heavy, linear full table scan to correlate fields, degrading performance to ON complexity. By extracting and virtualizing the key attributes into isolated, memory map indexes, our search lookups drop to a constant O1 complexity, shielding the data layer from massive traffic spikes. However, forcing structured transactional data and unstructured natural text into a single index model causes a different bottleneck, the single index ceiling. Heavy text scoring operations create massive cache evasion, constantly throwing out lightweight order metrics from the execution cache. This leads to the severe thread blocking on the shared index lock. By completely splitting our data into separate indexes, we unlock three core benefits. First, a concurrent execution. Isolated nodes run such routines simultaneously, completely avoiding synchronization bottlenecks. Second, isolated failures. If policy scanning hits high latency or crashes, order lookup stay fully operational. Third one, optimal serialization. Keeping order mode memory small and compact boosts query speeds to real-world microsecond threshold. Looking at our high-level architecture, we use Fast API as our entry gateway, RabbitMQ as our distributed nervous system, and an Elasticsearch cluster as our high-speed data warehouse. The data flows from the user interface is broadcasted via a Fanta exchange to independent background workers. Then this is finally aggregated by our master node for Gemini AI reasoning. Let's look at how we ingest and handle this traffic securely. Now, let's move into the part 2, ingestion and messaging. The asynchronous message lifecycle follows a highly decoupled path. First, the user client hits our API gateway, which instantly assigns a unique correlation ID and trace ID. Second, the master publishes the payload into the RabbitMQ dispute exchange. Third, this exchange instantly counts and broadcasts the message to the order queue and policy queue for parallel ingestion. Finally, the workers send the findings back to the exclusive callback queue, where the master aggregates data via correlation ID matching. A vanilla message broker set up with our fallback configuration can suffer up to 70% message loss during the server outages. Our system implements an active dead letter queue safeguard to achieve zero data loss, defined with a tight 10-second time to live inside a config.py. Any critical worker crash or infrastructure timeout automatically triggers an asynchronous message queue pipeline basic NAC with recur equal to false. The broker then reroutes the message via a dedicated dispute DLX to isolated dead letter queues for admin inspection. Let's look at part 3, our Elasticsearch database layer running on the virtualized Docker container slots. To optimize search speeds under load, we separate numerical metadata such from text matching using two clean index schemas. In orders metadata and the order code fields is mapped at a strict keyword type to bypass heavy text analysis. It also maps the purchase date as a native date type, which the LLM uses to audit the platform's 7-day return window. Meanwhile, the return policies index maps categories to a keyword type and long-form policy documents to a text type. Because our indexes are isolated, our background workers apply completely different search mechanisms. Worker order relies on a strict term matching, processing extract strings lookups with an average latency for under 15 milliseconds. The worker policy applies a hypersemantic fallback. It first runs a direct category filter. If that fails, it instantly falls back to full text natural language text analysis using Elasticsearch native BM25 radius scoring with an average latency of under 25 milliseconds. As shown in our latency share breakdown, gathering this distributed context takes less than 45% of our entire execution window. Thanks to parallel execution, our data gathering finishes in under 50 milliseconds. This optimization leaves the remaining 55% of the time window wide open for the rich, generative semantics reasoning of our Gemini LM layer. Let's look at part 4, Gen AI and the masternode. The standard share message channels easily block under heavy concurrent loads. To fix this, our version 4 master API initialized an entirely decoupled RPC sessions for every single transaction. Each API query builds and tears down its own isolated RabbitMQ channel natively, eliminating synchronization locks and enabling rapid concurrent execution. Mathematically, the masternode acts as a set union operator, aggregating context from different nodes into a unified prompt computed as C total equal to C order union with C policies union with C complaint. To guarantee absolute reliability, we engineer free strict zero hallucination guardrails directly into our system. First, simulated date lock. We synchronize a global simulated date string across all runtime schemas to force accurate mathematical evaluation of the 7-day platform window. Second, deterministic JSON, strict system instruction and regex pattern matching force the Gemini model to output only a clean two-property JSON schema containing status and reason. Third one, anti-irritation rules. We hard-coded hygienic clauses directly into our prompts. For example, if a product seal is broken and intimate items like lingerie or beauty, the AI is instructed to issue an immediate absolute rejection based on a platform law, eliminating moral hallucinations. Now, let's move away from the slides and watch our system handle these workloads, guardrails, and infrastructure failures in a live demonstration. As we step into our live technical demonstration, let's first observe our system core integrity through the master gateway's health telemetry endpoint. As displayed in this live JSON string, our non-blocking I/O connection pulls to both RabbitMQ and Elasticsearch are 100% active. Both background worker daemons are up and listening for incoming traffic. Switching to our Streamlit application, our database metadata is cleanly seeded, establishing a perfect boundary between our active orders and status return regulations. Let's run our first transaction using a valid record order auth001. The customer is claiming a critical product malfunction. As I trigger the evaluation, please keep a close eye on the two background worker terminals on the right. Notice that both windows flash at the exact same milliseconds. Because the master node dispatches tasks asynchronously via an asynchronous message queue pipeline FANA exchange, The message is conned and sent to both queues simultaneously. The worker order grabs the transaction data while worker policy carries the policy rules. The master node aggregates these payloads using the correlation ID validation, and the Gemini model correctly detects a real manufacturer defect within the valid time window, guaranteeing the secure approved decisions by zero-thread blocking. Now, let's challenge our system guardrails. For case 1, I will submit order 002 using polite, persuasive language to ask for a clothing exchange. However, the system immediately returns a strict rejected decision. The policy worker determined that his worker was bought 15 days ago. Since the clothing category enforces a strict 7-day time lock window, the guardrail triggers an immediate denial blocking semantic social engineering. For case 2, let's submit order 003, which belongs to the lingerie category. Even though the customer claims they only tried it on, our system retrieves the strict platform health rules. Intimate clothing cannot be returned once opened for consumer hygiene protection, because the AI is structurally bound to the facts fetched from Elasticsearch. It cannot hallucinate and issues an absolute rejection. For case number 3, let's look at order 005. Watch how fast the rejected verdict pops up on the screen. It is instantaneous. This proves our early exit circuit validation logic. The database shows this order status was already cancelled. Since cancelled transactions are completely ineligible for returns, our gateway stops and requests immediately, acting as an API cost shield that saves token wastage on desk business logic. An important refinement in our architecture is how we separate a simple user error from an actual infrastructure failure. When I submit a non-existent code like ORD999, the worker order executes perfectly but returns an empty database hit. A user typo is a valid business logic miss, not a system failure. Therefore, the worker issues a standard basic ACK to clear the message from the main queue. If we open our administrator dashboard and check the dead letter queue monitor, you can see the pending quarantine count is still exactly 0. User typos never contaminate our operational recovery queues. Finally, let's validate our cluster's fault tolerance by injecting a live infrastructure failure. I will manually queue our order metadata worker processing using Ctrl+C. Now, watch the front end as a customer submits a new transaction. The interface doesn't freeze and the gateway doesn't crash. Thanks to our isolated channel design in version 4, the master gateway handles the broken service safely, waits for exactly 5 seconds. Our configure RPC timeout limit, and throws a clean fallback error to the user to prove that we lose 0 data. Let's check our RabbitMQ data queue on the admin dashboard. As you can see, the exact request that timeout is perfectly trapped and preserved inside the order DLQ isolation vault, complete with all its original headers intact. Our endpoint executes a non-destructive transaction check using basic get and using basic net with req equal to true, allowing us to safely audit the raw JSON payload on this dashboard without removing it from the broker. Once the worker process restarts, this message will be safely reprocessed with absolute transaction durability. Now, to wrap up our technical session, let's look at the foundational documentation and standards that guide our implementation. As shown on this references slide, our entire system design isn't built out of nowhere. We strictly follow Martin Fowler's classic enterprise architecture patterns to handle our high concurrency routing. For our network messaging, we implemented official Fast API asynchronous web routing and standard RabbitMQ protocols to guarantee that data ingestion can absorb massive transaction peaks. Finally, our storage optimizations relies on the Elasticsearch reference manual for log-free multi-index queries, while our alignment uses the latest Google Gemini API specification for robust structured JSON outputs.